From the Library of Congress in Washington, D.C.
Good morning. So let's get started. So welcome to the 75th Topics in Preservation Series lecture, or TOPS lecture. My name is Elmer Huseman. I'm the Chief Conservator here at the library. And it is my great pleasure to make some introductory remarks for today's presentation given by Dana Hemingway and Matthew Clark, titled Removing Residual Iron from Platinum and Palladium Prints. Before I do so, I would like to welcome our more than 70 colleagues who are tuning into our live web feed. And for those who cannot join us live, the library is recording today's presentation and will make a high-quality video or on-demand video stream available for both the library's main website and the preservation site in the coming months. In the meantime, we invite you to visit our website to keep abreast of our upcoming lectures and other ongoing work. And should you wish to receive announcements from us, visit loc.gov and click on the orange RSS icon to sign up. All right, so now that's out of the way, we can actually focus our attention on the talk. Photographic material that Dana and Matt will be talking about are of great interest at the library and to others with collections that hold platinum and palladium photographs. These photographs were extremely popular just before and just after the turn of the 20th century, and they played an important role in the rise of photography as an art form, as well as being one of the predominant processes that documented the visual world at that time. While these photographs are often considered permanent and quite stable, we know from examining our collections that unfortunately the condition of platinum and palladium photographs can deteriorate over time. Dana and Matt's work is a wonderful example of the research we do to understand the object's condition, determine why it may be deteriorating, propose treatments to improve its condition, and evaluate the efficacy of those proposed treatments. The ability to preserve collections for future generations, that is our charge, depends on our knowledge of that deterioration and how to arrest or correct it. So as for Dana and Matthew, Dana Hemingway has been a senior photograph conservator at the library's conservation division since 2003. She serves several special collection divisions and as the conservation liaison is responsible for preparing all photographs selected for in-house and outgoing loans. She's currently researching and treating the library's important collection of copyright deposit prints of the earliest motion pictures. Before coming to the library, Dana was an Andrew Mellon Fellow at the Metropolitan Museum of Art and participated in the first cycle of Advanced Residency Program in Photograph Conservation, co-sponsored by the George Eastman House and the Image Permanent Institute. Dana has a master's degree from the Winterthur University Delaware program in art conservation, specializing in the conservation of photographs. Dr. Matthew Clark is conservation scientist at the Freer Sackler Galleries at the Smithsonian Institution. He has been working in the field of conservation science since 2010, when he joined the National Gallery as a photograph material scientist as part of a project funded by a grant, also from the Andrew Mellon Foundation, focusing on the study of platinum and palladium prints. This work has involved the application of spectroscopic, microscopic, and reverse engineering techniques. Before his work at the National Gallery, he investigated optical imaging techniques and methods and analyses at the National Institute of Standards and Technology. Matt has a PhD in analytical chemistry from the University of Michigan. Please join me in welcoming Dana and Matt.
Thank you, Elmer. The following presentation is a collaboration between two neighboring institutions with common goals and interests. It began, like much recent platinum photography research, under the auspices of the National Gallery of Art's Platinum and Palladium Initiative. Matt presented preliminary results of our research last November at the project symposium in his discussion of the technical history, chemistry and degradation, and analysis of platinum and palladium prints. This talk will review and expand on key elements of that discussion and present results from research conducted since then. We will conclude with an assessment of advantages and disadvantages of chelation as a conservation treatment. The list of photographers who worked in platinum in the early 20th century is a who's who of the pictorialist movement, some of whom you see in the image on the screen. Others include Imogen Cunningham, F. Holland-Day, Frederick Evans, Alfred Stieglitz, and Paul Strand. They all worked and loved the medium. As Stieglitz wrote, the platinum print has an indescribable charm, suggesting atmosphere, though the negative printed on another medium may be entirely devoid of this pictorial quality. Today, the increasing number of exhibitions and academic study that include platinum photography demonstrates our own esteem of the medium. The Platinum Palladium Initiative has unquestionably heightened our awareness and increased the knowledge base of this medium. While this project was taking shape, here at the Library of Congress, I was considering treatment options for a Laura Gilpin photograph. Upon examining the print, I was struck by the degree of darkening on the recto, especially when compared to the verso. This Clarence white print, on the other hand, is stained on both sides. While this photograph contains overall staining, as well as localized dark spots. And I think you'll agree that this Paul Outerbridge appears to be in very good condition. So what are the sources of staining and deterioration? It interferes not only with our appreciation of the image, but can cause extreme brittleness, making the print vulnerable to physical damage. The old adage, a platinum print is as permanent as its support, was probably meant to be reassuring. There are a number of possible sources for poor aging: platinum-catalyzed paper degradation, acid-catalyzed hydrolysis of cellulose, photooxidation of cellulose, and residual processing chemistry. There. This series of images illustrate the steps in the process of making a platinum print: sensitizing the paper support, exposure to UV radiation, and image development. The simplified chemical equations show how light-sensitive iron salts are used to reduce platinum to its metallic state, thereby creating the image material we see in the print. Final processing includes acid clearing of unused sensitizer and extensive washing. If the remaining iron compounds are not adequately removed from the print, residual iron can go on to produce colored compounds such as iron oxide and hydroxides, and induce further future degradation of the cellulose support. This will cause yellowing and loss of paper strength. One can quickly imagine a number of factors that lead to incomplete clearing of prints. First, proper processing takes over an hour to finish. If there are multiple prints in a single bath, they would need agitation to be adequately exposed to the processing chemistry. And finally, that chemistry, if not replenished, may become exhausted and not fully able to clear unused sensitizer. Inevitably, mistakes were made and shortcuts were taken. And of course, the condition would be made worse if the print has been stored in a poor environment since creation. Our study is based on the assumption that residual iron causes staining and paper degradation, and removing that iron will benefit the print's preservation and aesthetic appearance. Historically, conservation literature reveals a number of approaches, including acidified bathing solutions and powerful oxidative bleaching. The use of chelators for paper conservation applications was discussed by Helen Burgess in 1991. Since then, there have been an increasing number of studies dealing with the corrosive action of metal complexes on cellulose, such as iron gall ink, a study we do a lot with here, and copper pigments as well. To date, there has only been one published study by Ghent and Rees in 1994 that directly involves chelating iron stains in aged platinum prints. When developing strategies for the current study, a number of factors or questions help guide our approach for testing chelators. What delivery method would be most effective? Immersion, blotter washing, application of gels? Could we select chelators that are selective for iron? Could we select chelators that would not necessitate extremely elevated pH levels to activate? Would there be a collateral loss of original material on the print, that is, platinum, the image material, or calcium incising that's in the paper? What chelator concentrations would be safe? Would the reported long bathing times be necessary? How long would it take to remove the chelator, and could it be completely removed? And finally, is this procedure practical for conservators? Matt will now address how we incorporated these factors into our research questions and strategies.
Right, so as we wanted to look into this research and we want to find out whether chelation treatment is something to be considered, we first want to think about how does residual iron affect a print's appearance, and does chelation both improve the removal of iron and change the print appearance. And finally, one of the main parts of the research is we wanted to find out what's the long-term effect, because this is probably the most understudied component. Now, there's a challenge here, is either we have to find a large number of historic prints in which we think we know how they were made, or we have to make our own prints where we can control at least most of everything that goes into them. And so that's what we decided to do. Handily, as part of the Platinum and Palladium initiative, there's been a lot of research at the National Gallery of Art and at other institutions at making platinum and palladium prints. So shown here is Christopher Manus making up solutions for platinum printing. And through the course of the whole initiative, there's been hundreds, or possibly now into the thousand, of little different variables of step tablets that we've sliced and done at all sorts of different conditions. And so we can get this large range of different images and image qualities and then study them. But we first have to start with something to make the platinum prints on. And choosing an appropriate paper is a critical step. And early platinum literature would talk about you have to use a high quality paper. And so in this case, either a cotton or bast fiber paper was typically used. We don't want any a buffered paper. Alkaline buffered papers can interfere with the platinum printing process. We don't want optical brighteners, we don't want dyes, and the platinum process is better on starch or alum rosin sized paper compared to gelatin, and so that's the type of paper we're looking for. That's not easy to find. Most papers now have brighteners, they have different sizing agents than would have traditionally been used, but so we're at two different institutions and we can start getting through what we have available. And it turns out National Gallery of Art letterhead from the 1980s, roughly, has the properties that we want, and no one really cared if our team dug through and removed it from their closets. So that's what we've been using. We've had different lots of this, and it varies a bit, but we can use this paper as a good standard tool. And then we have to find out, well, what's a print going to look like in about 50 years, 100 years, and we don't want to wait. So we have to come up with an accelerated aging system. And that it's always its own challenge, but we are looking at using a few different techniques. What we settled on was we have the system where we have a stainless steel rig that we tie the paper samples to. That goes into a humidity aging oven. We age it at 70 degrees Celsius, at 75% relative humidity for 4 weeks. This is a condition that we found that generally minimized the paper degradation while increasing, with being favorable for the formation of stains. And they, by appearance, they mimic the stains that we had observed in historic prints. Now we want to do analysis on what happens to these prints. And so of course we look at these by eye and we can classify them that way. From my point of view as the scientist, we want to look at some quantitative measurements. So we're going to use two techniques. We're going to use X-ray fluorescence, and that's going to give us an idea about the elements. In this case, we're really looking at the amount of iron that's present in the papers. And we're looking at colorimetry, which will give us a quantitative value of how we perceive the print. And so we're finding out whether it's a brighter, darker, yellower tone print. So these are the main techniques I'm going to focus on here. Now, as Dana mentioned, the prints are made by applying the sensitizer to the paper. there are different types of staining that can occur in prints and in other objects. We're going to focus on what we call sensitizer stain. And that's going to occur in the region where we have the sensitizer was poured to. So you can see where that yellow ends, that's the end of the sensitizer, and we'll compare that region after development and processing to a region that never had any sensitizer on it. And we'll compare both prints that are aged and unaged, well processed and poorly processed. And so this stain exists even if the print was masked. And you can see on the far right that there's a tiny faint line that exists. We can enhance that contrast a little bit. And you can see it before aging, just barely, and then after aging it's more significant. So this is kind of our goal, because if a photographer made a print and it had a really bad stain, it probably wouldn't have come into the National Gallery of Art's collection, and probably may not have come into the Library of Congress. It all depends on, but so we're looking for shortcuts can be made, but that's going to still cause staining. So to do that, we have to do a whole lot of tests. And what was done by both Dana and I and by the broader Platinum team was to start taking shortcuts and find out what's the kind of least amount of shortcut you can do that's still going to cause a stain. So as a print goes from well processed to poorly processed, you will see more and more stain form, particularly after aging. But what you really can see is that you can take a lot of shortcuts, have a print that looks pretty good once it comes out of that final washing bath, but it's going to form a stain after a number of years. And the other question we want to know is, does the amount of iron also change when you do these shortcuts? And yes, as you go to more poorly processed prints, you'll see an increase in the amount of iron that's in the paper. So we know iron's important. We know it at least correlates with the image staining. So one thing I wanted to know in particular was, is iron enough alone to cause these stains, or do you need residual platinum or palladium salts also present? So is it a combination effect that you have platinum and you have iron, and then that is what's causing the staining? So one of the tests that we did was to make a quote-unquote platinum print, but without any platinum. So we added the iron solution, we sensitized the paper, we exposed it, we developed it, processed it otherwise with just this ferric oxalate and no platinum or palladium salts. And we still see staining. You can see a sensitizing line. On the top right, you'll see a paper before and after aging, and there's a kind of an orange line at the top. But the paper is changing color. And if we look at the XRF results, and again, we're using the XRF results to look at the amount of iron that's in the paper, we can see an increased amount of iron in the sensitized region compared to the unsensitized region for both this iron-only prints and for platinum prints. So we know we have residual iron in the paper. So iron's certainly a key element that's going on is here. We can quantify that color change. Again, we're using the colorimetry. So just quickly, I'm going to look at the LAB colorimetry values. The L value at the top is a measure of the brightness. So higher numbers are brighter paper. The A is a value of redness, greenness. Pretty much all their values are positive, which means as they go more positive, they're more red in appearance. Similarly, B is yellowness, blueness, and we're going to a more yellow print, so they're higher positive numbers. You can sort of ignore that and just look at the little bars here that show yellow or red. And the aged prints, they darken and they become more yellow. It's a simple kind of takeaway here. So if we know iron's related to the stain formation, can we remove it, and what does removing it do for us in the long term? So chelation treatments, as Dana mentioned, have been commonly used in conservation, and we know they're being used for photographs, but there aren't that many studies on what's actually taking place. So we should start and quickly review, well, what is a chelator? It's a molecule. It can bind to multiple sites on its target ion. I like to think of it as kind of a hand holding like an object. So it has these multiple sites where it can bind, and that makes it's a strong affinity for certain ions. Depending on the pH of the solution and other conditions, that can change which ions it will bind more. It's not specific to iron, but it can be more specific. Some molecules can be more specific than others, and I'll talk about that a little bit. But there are different forms of iron. Iron 3 state, iron 2 state, and each chelator can have its own binding coefficient for each state of iron, and that can change with pH. So the very, very common chelator is EDTA, and at low pH it'll bind more iron 3, and at higher pH it'll bind more iron 2. Based on the conservation literature, we chose 3 chelators. I'll skip going through the full chemical names, but they are EDTA, DTPA, and HBED. EDTA was invented in the 30s and has been very commonly used. You'll see it in many different applications, from conservation to gardening. DTPA is very structurally similar. It's the one on the right to EDTA. It has a higher binding coefficient for iron than EDTA, but it's also less soluble. And then HBED is structurally a little different. It has a very, very strong binding coefficient for iron 3, and so it's had a lot of interest recently in the conservation community because in these age prints we expect most of the iron to be in the iron 3 state. And I'll talk a little bit more about each of these as we come to them. So we're looking at these 3 chelators, and based on the other literature, we also know that the addition of a reducing agent, in this case sodium dithionite, is often used in order to change one form of iron to the other, in this case changing it from the iron 3 to the iron 2 state, and that can aid with the removal of iron by the chelators. And we tested 2 pH conditions that would be amenable for conservation treatment, pH 6 and pH 8. After our initial test, the pH 8 gave the better visual results, and so we stuck with that. Plus, all 3 chelators are more soluble at pH 8, and especially for HBED and DTPA, that was very helpful. So we start with a custom negative, and we do this because we want a large area where we can form that sensitizer stain, and that's going to form in this masked area, or this D-min area, and we can compare it with this large unsensitized area. This is something that you don't necessarily find in the prints in our archives or artistic prints, because either the paper was initially sensitized throughout the entire sheet or it was trimmed after it was made. So that's hard to compare, but this gives us a really good sense of what's happening. And then we compare these thoroughly processed prints to poorly processed, and then we age them in cycles. So we compare an unaged, aged, and a print that has been aged 2 times and see that it continues to darken. Both the well-processed print and the poorly processed print do change in appearance over time, but the poorly processed print changes more. Now for our chelation tests, what we want to do is we want to take the print after 1 aging cycle, and you then treat it, and then we will re-age it to find out what happens after that. So in the basic initial test that we did, we first hydrate the prints in water for about 10 minutes. We did a 2-hour chelation treatment, and then we washed it in a pH-adjusted water for 30 minutes with multiple changes of the water, and then we looked at them. And I think this is, in the lower right it shows you chelation is not a really exciting treatment. And a lot of this stuff, you don't want a treatment that's going to run away from you, right? So at least here, we could sit and watch it and rock trays. That. So what do we find from our initial results? Well, the paper sizing is important. We did compare gelatin-sized paper to alum rosin-sized paper, and the gelatin retained more iron. The chelation treatments did remove more iron than a water treatment alone, and that's important to note. And as we increased the chelation time, so if we went to 4 hours, we saw an increased benefit. There wasn't much benefit after 4 hours, but we thought we could also exchange new chelation baths and improve the process. So that's something else we plan to explore. Adding a reducing agent did help removal of iron for both EDTA and DTPA, but it did not for HBED. That shouldn't be a surprise because HBED is really specific for iron 3, so there's no real reason to try to reduce iron 3 to iron 2 for an HBED process. And I'll talk a little bit more about HBED in a few slides, but HBED we found was very difficult to remove from the prints, and so we planned some more experiments on how to aid its removal. Okay, so we did a whole lot of tests after this, and I'm not going to go into great detail, but we looked at different concentrations of chelators. We looked at increasing the chelation time as well as exchanging multiple baths and the absence or addition of a reducing agent, in this case the sodium dithionite. And we looked at the concentration of sodium dithionite from 2% to 8%. And then I had to do analysis on all of them. So that takes some time too. So there's a whole lot of data here, and I'm not going to go through all of this. I'll kind of show you in general what we saw, and then I'll go through a couple of specific cases. But the amount of iron in the prints, as they were more poorly processed, will show a greater, you can see a larger amount of iron. The chelators all reduced the amount of iron that was present. In general, the addition of the dithionite further aided the reduction of iron. In no place is this going to remove all of the iron from your prints, and that's pretty important to note. And there's some different forms of iron that were in the paper before it was even made into a platinum print, before the sensitizer was added. And we can compare this with the colorimetry results. As the print ages, it gets darker. It also gets yellower. All the chelators generally bumped up brightened the paper a little bit. Dithionite tended to also further brighten the paper. And you may notice on the far right, something's going on with HBED where it looks a little bit more red. So we kept an eye on that. So don't try to keep all of this in your head, but let's just look at one sample. So let's look at EDTA. And in this round, again, we're taking this sample that's been aged once, and we have a whole bunch of these, and then we do different chelation treatments. So in here, we're generally going up longer chelation times and exchanging baths and adding dithionite to it. And it's a little difficult to see, but generally, as soon as you do the chelation treatment, the print is brighter. After you do aging, it darkens some, but not to the extent as if you had not done the treatment. The really high concentrations of EDTA were not very favorable for treatment. This was essentially almost saturated, and so we had some issues with those. But we got some otherwise improved appearance of the prints. If we look and just focus on the iron content for the EDTA samples, we'll see that if you take that dotted line to be the amount of iron in the poorly processed print, after chelation, all of the prints had a reduction in the amount of iron. The addition of the dithionite further reduced it. But in the end, again, we're never removing all of the iron from the paper. We can compare these also and look at what else is being removed from the paper. So calcium is being removed from the paper, and that's not a surprise for anyone that's worked with chelators, and it's typical where calcium may be introduced during some conservation treatments. But that's not something we explored here. But we just note that calcium is being removed, and that's the case for all three chelators. We can compare these with the colorimetry results. Now, as I say, while this treatment isn't fast, it's also not so substantial that you see this, giant, thing where now it's this white, bright standard that of paper. That's not something that we're not aiming for that either. We're trying to improve the appearance from these stains. So the prints this is after aging. So the prints are of improved appearance compared to if they were not treated after aging. In all cases, we saw that they did brighten and they had a reduction in the amount of yellow. But they didn't make the print back to the state they would be in if they hadn't been properly processed to begin with. But they did improve them. We did a larger battery of tests with DTPA because from our initial trials it was quite, it was somewhat the most promising. As I said, DTPA is less soluble than EDTA, so it's at about 10 times lower concentration. It has about 100 times stronger binding to iron, so ideally it still can remove more iron. We did a large set of tests. They also, again, they brighten the paper. Some of that changes after aging. It does remove calcium, it removes iron, and the addition of the sodium dithionite improved the reduction of iron as well. We can compare that to the colorimetry results. And again, I'm going a little faster, just start to see all these plots, and it's hard to tell which direction things are going, but the dithionite seemed to brighten a little bit more when you had for DTPA samples than it did for the EDTA samples. And really in the DTPA we found samples where it has 2% dithionite and two-hour treatments to be the most amenable. And these are, again, all small changes. So this is, but just the conditions that we found to look the best both visually and by the measurements. So I alluded to HBED and that little bit of change in color. Now, one of the things that HBED is touted for is the fact that when it complexes with iron, it now has a color. And that was kind of interesting to see during the chelation treatment. The solution turns pink because that's the iron that's come out and it's chelated with the HBED. And so you can see something's happening. That's at least something different. And there's a little bit of tinge to the prints after they came out, even after multiple washes. But after aging, they become very pink. And so what's happening is, I suspect there's a small amount of HBED that isn't coming out because it's poorly soluble. And once it's in the accelerated oven, it's enough that it can complex with some remaining iron in the paper, because again, not all the iron comes out, and it forms this pink stain. We explored ways to remove HBED, and going from a 10-minute washing to 22 hours, and using buffers or a buffer or solution. And really, it was only after like the 22 hours that you couldn't tell that pink was there, and that's not really practical for most conservation treatments. It's certainly not an advantage of HBED to say, oh, it's really strong to remove iron, but you have to wash it for 10 times longer than the other processes. So that's all well and good, but you still have to show, well, is this relate to historically aged prints, so a naturally aged print? So we went through all our data, and I think this is a great slide of showing, like, we just would pore over the data and look at the prints and talk back and forth about what we thought was best. And we had a print here which shows a somewhat orangish appearance. It's a little brown. It's about the same thickness as the papers we're using, so that was somewhat handy, as we knew we can make about the same solutions and same time. And one of the first things we want to do is measure it by X-ray fluorescence to find out, is it a platinum print? Because you can't always tell, and that's an important factor to consider too. So we want to make sure it was platinum because we're focusing this work on platinum prints. And it does, and it has a lot of iron. So then we wanted to divide the print into 3 parts, have a control, do a DTPA and an EDTA measurement. We're kind of just kicking HBED off the list for now. And we want to do colorimetry and XRF measurements on areas of the print that are of similar density. And that's what this red areas are. That's similar optical density of the paper. And so these 3 yellow circles are where we did the measurements. And the print conditions we found to be most amenable the chelation conditions were EDTA for for a total treatment time of 8 hours with 3 different exchanges of the solution, and then the DTPA plus a 2% diethionite with a pair of 2-hour treatments. So we do see a reduction of iron, and we also see that the print is far less orange. It's a little bit brighter. We can look again, calcium comes out of the paper. A significant reduction of iron has occurred. What we saw here was DTPA removed more iron compared to EDTA, and it removed a little less calcium. So that was favorable. We also noticed colorimetry, it is brighter. We noticed there was a little bit of difference in the tone between the appearance. So the DTPA was a little bit cooler tone and the EDTA was a little bit warmer tone. That sort of surprised us. We don't know what the print looked like before it was aged, so we can't say that one treatment is more true to what the original intent of the artist was, but that was something that we just noticed. And then if we take this print and re-age it, we'll see that in the center, on the lower half, is what the print looks like if it was not treated and it was re-aged. So the print will continue to darken and become a little more orange. Both chelated portions also darken. They are not as dark as the print had it not been treated. And they are less orange compared to the original control of the print. Now, we didn't compare on that print water washing, and that's something we did want to explore because water washing is often used in conservation treatments of works on paper and on photographs for removal of iron, for removal of acidic products, and for strengthening of the paper. And so that's something we thought, well, maybe we do need to come back to it. We know from our earlier tests our water didn't remove as much iron, but perhaps there's some differences between our accelerated aging and the historic prints. So we had another print from our study collection that we examined, and we treated it by a DTPA and by buffered water baths. So we can see both for the water and the DTPA that the print has brightened. Some it's less orange. The DTPA, you do get this much brighter initial, this print. It's you lose a lot of that stained color, and it looks very sort of clean initially. It does darken after aging, but not to the extent as just the water washed alone. And so overall, we thought this showed that the chelator can remove both more iron and improve the print appearance. And we can look at the amount of iron. Certainly in the historic print, a lot more iron was removed for the DTPA treatments compared to the water treatments. And from here, Dana is going to summarize some of the advantages and disadvantages that we found.
Well, with this data in mind, I will highlight advantages and disadvantages of chelation for platinum prints. Chelation removes iron compounds from the print, as Matt has shown. It protects the print from future iron-induced deterioration and staining. This benefit may be mitigated, of course, if there is incomplete removal of iron, which could cause future weakening and discoloration. Alkaline aqueous immersion also removes acidic decomposition products and reduces discoloration. It brightens the overall print and restores tonal range. Disadvantages. You need XRF to confirm both the presence of iron and platinum before proceeding with the treatment. Our study really focused on platinum prints. If there are other toners or other image materials within the print, we didn't take that into consideration. They have other vulnerabilities, let's put it that way. If it's a platinum print, it may have different abilities to or become chelated in a way that you don't want. It removes material from the paper substrate, i.e. calcium and paper sizing. It potentially changes the surface texture of prints. If used, the dithionite reducer poses additional risk to the print during treatment. Any brightening of the print from the reducing capacity of dithionite may revert in time, as we've seen. And lengthy bathing puts the vulnerable platinum layer at risk, especially at the edges. And there may be unanticipated consequences to a chelation treatment that may be revealed in time. There. Finally, what are the different forms of iron in the paper? Initially, after processing, after aging, and are all forms a concern? How much calcium loss can be tolerated? Can it be effectively reintroduced? Is the treatment too aggressive for fragile prints? And how will modified paper, like japine, behave in immersion? We'd like to thank the Andrew W. Mellon Foundation for their assistance in the Platinum and Palladium project. I'd like to thank the Library of Congress for giving me time to work on this project. And we would like to thank the individuals listed on the screen. Thank you. Questions? Yeah.
Dana, did you consider a treatment where you would intentionally leave the chelator in? Not in the case of HBED, obviously, that gave problems, but, I mean, just some potential problems with papers like japine, you know, where you would have problems with the immersion.
With removing it. No, we didn't add that aspect to the treatment protocols, but it certainly is something that could be or should be considered. Got time? Other questions?
I noticed in the mapping exhibit in the main museum or the library, they had built a special case for the preservation, and it was an airless halogen lit chamber that was supposed to inhibit, I guess, the further iron accumulation and reversion of the initial treatment that they had done on the maps. How much does that forestall, does that significantly, those types of encasements, do they significantly forestall the subsequent, aging process after treatment any more or worse than they would if you didn't treat it and just put it in a preservation chamber without the additional iron removal?
Well, we're removing the oxygen, which would be the case in those exhibit cases, certainly would reduce oxidative chemical deterioration. That sort of treatment with the cases is reserved for particular objects within the museum. It's a very expensive and costly endeavor. It's not practical for all items. But certainly the less oxygen you have there, the less oxygen-related deterioration would occur.
So that
Would you agree?
is from the oxygen.
Not all, but some. Connie, you had a question.
Just one comment regarding the paper that you guys used to test all of these, variables. It's probably the best possible paper support available that we could find. And with all of the crazy stuff that they put in so many different papers, especially modern platinum and palladium prints, it's a daunting consideration to think about what the implications are based on crazy synthetic sizes, fillers, etc., colorants. So, in other words, what you guys have done is phenomenal, and it's only one paper.
Yeah. Absolutely.
So that's just a cautionary remark.
Right. Yeah, it's a challenge, certainly, for...
You guys deserve great credit for looking at this because it is eye-opening.
Absolutely. Yeah, John.
On that, does this process demand that the paper be sized initially? I know you're using it because these were sized papers, but that, if not, that'd be an interesting thing to look at because then you would determine the role of your rosinous acid in the rosin alum sizing or that protein in the gelatin.
Right. Well, the main advantage is if you don't have a sizing in your paper, when you sensitize it, it's just going to soak it up, and you won't. It's going to be very expensive, essentially, because really you're going to be forming that platinum image near the top, and it's also it'll be almost impossible to even coat the paper well. We've tried a lot of different in the broader project, a lot of different ways of looking at different papers, and things like unsized papers are not favorable for that.
And it's also not that typical of historic prints. They would have sizing. Yes?
So curious, it's been a while since I thought about rates of chelation, but in solution, my memory is that EDTA, for example, chelates very, very quickly. And the times that you were looking at were pretty expensive, but the paper that you're working, it seems like it would get saturated reasonably quickly. So what is causing the reduced rate of chelation that's requiring that extended period of time to rot your trays?
I mean, I think some of it does take some time for the chelator to kind of permeate in and bind and then to come out. Because you can slowly, just watching it, we do see over the hours that we'll see the change. And so that's kind of what we're basing it on. I don't know, some of these, the iron compound isn't just in solution, it is somehow bound within the paper fibers. And so that is what I think it takes the time to get in and eventually out and then washed away.
Any other questions? Yes?
Is iron entrained in the high density areas of the print when it precipitates?
There's different, there is a higher amount of iron total in the darkest areas of the print. Whether it's because it's been entrapped and it's more difficult to get out, I don't know. But usually in the measurements we'll see that it's there. I think also some of it, after it's been gone through this photo reduction process during the exposure, may make it more difficult to remove. So the paper test that I did with only the iron present, you could tell a difference, because we put it in the same step tablet. You could tell that there was a little bit more iron in the area that received more light. But that's kind of an initial little test, and I don't know exactly how accurate it is. It was enough to show here, and people have seen that in other studies where you see more iron in the densest areas of the print.
But then the staining will be less obvious there too. Any other questions?
Yes. For us practicing platinum and palladium printers, should we consider adding DT to our EDTA clearing baths? If so, what concentration? What might be the risks?
I think usually there are practitioners that will use a reducing agent in clearing baths, but usually that hasn't been sodium dithionite. Sodium dithionite is a stronger reducing agent, so it's been more often used on the treatment side, but something like sodium metabisulfite has been used to remove iron from prints. And that's often done in conjunction with in EDTA baths in particular.
You could also, some of the best clearing bath that we have found doing all of these experiments has been for modern platinum printing, has been to use a disodium EDTA clear bath first, which will remove all of the Fe2, and then going to the sodium disulfide, which will then reduce everything to Fe2, and then using the final clearing bath of EDTA. So yes, something other than sodium dithionite, but using a reducing agent in between the two different
Thank you very much.
This has been a presentation of the Library of Congress. Visit us at loc.gov.